Okay, today's video is on multiple linear regression. So multiple regression equation is a prediction equation that's linear, and it's between a response variable and two or more predictor variables. So two or more independent variables and one response variable. The coefficient of determination is a multiple coefficient of determination. It's r squared modified to account for the number of variables in the sample size. Can't just have an r squared based on one. We're going to have an r squared based on the number of predictor variables or independent variables we have in our model. So when you have more than one variable, you need to make sure that all of your variables are going to make your model as accurate as you can. So you have to use common sense. You have to consider the p-value. Once we have our printout, we're going to consider the p-value, and we're going to have an equation that has the best overall significance. We're going to consider equations with a high value of the adjusted r squared, and we're going to pick the equation that has the largest r squared. So we have to take out sometimes we have to take out some of the predictor values or some of the independent variables. Sometimes we think they are going to have an effect on the response variable, and it turns out that they don't, so we would want to eliminate those. And another reason we would eliminate them is if a pair of variables had a correlation with each other. You wouldn't want, for instance, if you were looking at the percentage of body fat in someone, you wouldn't want your two independent variables to be skin fold thickness on your tricep and skin fold thickness on your waist, because those are going to be correlated with each other. An increase of one is going to have an increase in the other, and that causes them to interact with each other. So you would want to get rid of one of them. You would exclude the one with the lower value of r. So in our first example, we have an engineer wants to develop a model to describe the gas mileage of a sport utility vehicle. Data is collected from 15 vehicles regarding the curb weight, engine size, number of cylinders, final drive ratio, ground clearance, and miles per gallon. Whew. Let's see, that is 1, 2, 3, 4, 5, 6. No, 5 variables. All right, and so the first part of the question is asking us to write a first order model as a function of curb weight, engine size, cylinders, drive ratio, and clearance. So our equation, our y, our predicted y, or our mileage as a function of that is, we're going to take the coefficient from each of these regression analysis up here, and we end up with 0.00002 5x minus, I just crossed that out, I didn't mean to, 1.27 x2, this is x1, minus 0.231, that's x3, minus 1.77, that's our x4, minus 0.101 that's our coefficient for the clearance, x5. So that is the first order model. The second part of the question asks us to explain the meaning of beta, B0, B1. Remember, beta is a parameter. Parameter is the value for the population. A statistic is the value for the sample. Since we can't always, or most often can't get the value of the population, we take a sample, hence the need for the study of statistics. And then B0 or beta 0 is the y-intercept of our population. And then beta 1 is the slope. For our population, it's also, in this case, it is curve weight. So we're going to figure out the overall utility of our model, and we're going to use a significance level of 0.05. So when we do this, we're going to write a null hypothesis, and we're going to say that B1 equals B2 equals B3 equals B4 equals B5 or beta 5, and all of those equal 0. These are my beta values here. All of these are my beta values. Well, not the constant. Remember from the previous section that when the beta is 0, there's no correlation. When there's no slope, there's no correlation. So that is our null hypothesis. And our alternate hypothesis is that at least one beta is different. And that would mean there's some correlation. We can look at the F statistic too. Our F statistic is calculated by, I'm going to write this up here. It's our R squared divided by 1 minus R squared times n minus the number of categories plus 1 in parentheses divided by the number of categories. That is what gives us our F statistic. Our printout already has that, so we don't have to calculate that by hand. But if we have a large F statistic, that's evidence against our null hypothesis. So our F statistic is 6.34. We have to be careful, though, not to use just the F statistic. It's just an indication. We're actually going to use our p-values because the more variables I have, the lower my F statistic gets. And so it's not the overall end-all be-all. So my regression p-value is 0.009. So if I look, F is 6.34, which is a decent size F value, and then I take my p-value, 0.009, and I compare that to alpha. Alpha is, actually, we should look at alpha over 2 since that's our alternate hypothesis, is 0.025, and we compare them. Well, our p-value is less than alpha, so we would reject HO, our null hypothesis. And so overall, we have some validity to our model. Okay, the coefficient of r squared and the adjusted r squared. When we have more than one variable, we're going to use the adjusted r squared, and that just means that is up here somewhere. There we go. It's 65.6%. That means that 65.6 of the variation of gas mileage could be explained by the model, or is explained by the model. That also means that 34.4% is not explained by the model. So let's look at the last part here. Conduct a hypothesis test to determine if curb weight is a useful predictor. So that hypothesis test on the individual variable of curb weight would be that B, which one is that for us? That's our first one, beta 1 equals 0. And the null alternate hypothesis is that beta 1 does not, oops, that's a 1, equals 0. And here we have a p-value, an individual p-value on the curb weight of 0.978. That is greater than alpha over 2. So we would fail to reject. And we would eliminate that variable from our correlation. So we would be down to 4 variables after that, because that's not a useful predictor. And we don't want that in our equation. All right, second example. A realtor wants to find a model that relates the asking price in thousands of dollars to the square footage, number of bedrooms, and number of baths. And we have a mini tab printout below. So the first order model for the asking price in thousands as a function of square footage, number of bedrooms, and number of bathrooms would be, I'd take my coefficients. Well, here is, I think I forgot to put the constant on the last equation, but the constant goes in also, and we have the coefficients, and we have for square footage, I'm rounding it to 0.072. That's my first x value, minus 0.81. That's my second x variable, plus 55.35. That is my third x value, or x variable, slope for my third x variable. So the coefficients here is that as for the first x variable, as square footage goes up, the price also goes up. And for the second variable, as the number of bedrooms goes up, the price goes down. And then the third one, as the number of bathrooms goes up, the price goes up. Well, if we think back to the first slide where I said you have to use your common sense, it doesn't make any sense that if the number of bedrooms goes up, the price goes down. So I'm thinking there's something fishy with this one. But let's conduct a test of our model at a significance level of 5%. So with 3 variables, our null hypothesis is going to be B1 equals B2, beta 2 equals beta 3 equals 0, and our alternate hypothesis is going to be that at least one beta is different. Or doesn't equal 0. And since alpha, and we can look at our F statistic too. F is 5.72. That's pretty good. And then our p-value is 0.018. So p, since this is a two-tailed test, alpha would be 0.025, and 0.018 is less than 0.025, so p is less than alpha, so we would reject our null hypothesis. This is a useful model. The standard deviation of the error term, you'd find that here. That's 46.2441. Okay. Are the bedrooms a useful predictor of the asking price? So we're going to say that is our second beta. So our null hypothesis is that our second beta is 0. Our alternate hypothesis is that it's not. And so alpha over 2 is 0.025. And if we look at our p-value for bedrooms, it's 0.977. So no, we would fail to reject our null hypothesis, and we would eliminate that variable. Not significant. So that's just a little bit of an intro, a small intro into multiple regression.